Hello, am I audible?
I am class level to
Am I audible?
Yes, ma'am.
Yes, ma'am.
Good morning, all. Today, some technical problem we got late.
Good morning,
We
ma'am.
start. The corrections that I have gave you yesterday, have you written that? Okay. Now see the next theorem. This is the last theorem under this title. The set V of xy, that is set of all bounded linear operators from x to y. The set V of xy of all bounded linear operators of x into y is Banach space if y is Banach space. This first statement only write. Don't write the second. Proof. Let Tn be any Cauchy sequence first write let B of x comma y, that is set of all bounded linear operators from x to y, be a space of all bounded linear operators of x into y. This will be the first statement. We have to write first what we have given. Then write sequence Tn be any Cauchy sequence in V of x comma y. X and y are non-linear spaces. So by Cauchy criteria that we have written, you can write the epsilon delta definition also. By that method also, you can prove the theorem. Here directly given that norm of Tm minus Tm tends to 0 as n tends to infinity. You can use epsilon delta definition also. Norm of Tn minus Tm less than epsilon whenever n comma m greater than some integer n. So for each x belongs to capital X, we have norm of Tm of x minus Tn of x. is equal to norm of Tm minus Tn of x. Don't write here T is linear. This is by any general property of any function. This is less than or equal to norm of Tm minus Tn into norm of x. And this converges to 0 because Tn is a Cauchy sequence. Or you can write here less than epsilon also whenever m, n greater than an integer n. By both methods you can prove. So the sequence Tn of x. For a fixed x, we get a sequence of images of x under different linear operators. Tn is a Cauchy sequence in y. By definition of Cauchy sequence. But y is a Banach space. Don't write here, but y is a Banach space. Yes, you can write here. You have to write here, but y is a Banach space. That is y is complete. So there exists an element Tx in y such that Tn of x converges to Tx. We have given that y is a Banach space and we are proving that set of all bounded linear operators B of xy, it is a Banach space. So write the second statement also given in the theorem. If y is a Banach space, then set of all bounded linear operators from x to y, this is also Banach space. You have to mute your mic. Raksha Gulhane, mute your mic. Hence, limit n tends to infinity, Tn of x is equal to Tx. All of x belongs to capital X. This and Tx belongs to capital Y. To show that T is linear. If we show T is linear and bounded, then T belongs to B of xy, and it is proof that the Cauchy sequence Tn is convergent. And the limit lies in B of xy. Hence, B of xy will be a Banach space. It will be complete. Now we prove that T is linear. T of alpha x plus beta y is equal to limit n tends to infinity. Right here, limit n tends to infinity. Tn of alpha x plus beta y. This is by 2. Is equal to limit n tends to infinity. Tn of alpha x plus Tn of beta y, because T is linear, is equal to limit n tends to infinity alpha into Tn of x plus beta into Tn of y, because T is linear. Alpha into limit n tends to infinity Tn of x plus beta into limit n tends to infinity Tn of y. Alpha and beta, these terms don't contain n, so we can put them outside the limit. Is equal to limit t of x is equal to alpha into t of x plus beta into t of y, because limit n tends to infinity Tn of x is equal to tx, and limit n tends to infinity Tn of y is equal to ty. Hence, it is proof that t is linear. Now we show t is bounded. When you read this theorem, you will get cleared all things. To show that t is bounded, we have to show that norm of tx is less than or equal to some constant c into norm of x. For any x belongs to capital X, we get norm of tx is equal to norm of limit n tends to infinity Tn of x is equal to limit of norm of Tn of x. Limit can come out of norm. This is less than or equal to limit n tends to infinity norm of Tn into norm of x. Because Tn are bounded linear operators. We have taken this sequence of bounded linear operators. So for every n, Tn is a bounded linear operator. So we can write here less than or equal to limit norm of Tn into norm of x. Because norm of Tn of x is less than or equal to norm of Tn into norm of x. This is given in the notes that I have given to you of last two lectures. Less than or equal to supremum of norm of Tn into norm of x. We give this equation number 3. If we can prove here directly that limit Tn is equal to t and less than or equal to norm of t into norm of x, that I will tell you later. But now we see the method given here. Also we have mod of, right here mod of norm of Tm minus norm of Tn less than or equal to norm of Tm minus Tn. Here it is given Tn minus Tm. Norm of Tn minus Tm. This converges to 0 as n tends to infinity because sequence Tn is Cauchy sequence. You can use epsilon delta definition also. This implies sequence Tn is convergent. And thus bounded. We know that sequence of that is norm of Tn. Okay, thus it is bounded. So there exists a real number k greater than 0 such that supremum of norm of Tn less than or equal to k. We give this equation number 4. From 3 and 4, we have norm of Tx less than or equal to k into norm of x. Hence, T is bounded. Hence, T is bounded linear operator. T belongs to B of x. So that is set of all bounded linear operators from x to y. And hence, B is a Banach space. Now we have to prove. It is not proved here that B is a Banach space. Now we have to prove that Tn converges to T. The third part of theorem is not given to here. I will give you in notes. We have to prove that Tn converges to T. Yes, we have proved that Tn converges to 2 in first part. Here. norm of Tm of x minus Tn of x less than or equal to norm of Tm minus Tn into norm of x. Hence, Tn of x is a Cauchy sequence which converges to T of x. As norm of Tn of x minus Tx is less than epsilon, here we have written norm of Tm of x minus Tx because it converges to Tx. Tn of x converges to Tx. So that norm of Tn of x minus Tx less than epsilon. So that supremum of norm of Tn of x minus Tx, where norm of x is less than or equal to 1, is less than epsilon. So supremum of norm of Tn of norm of Tn minus T into norm of x less than epsilon. So supremum of norm of Tn minus T is less than epsilon. So norm of Tn minus T converges to 0 and Tn tends to T. This part, these 4 steps you have to write after these steps. That is why I don't give you the notes of first chapter directly. Not only first chapter of any chapter, because there are corrections in different theorems. In preparation of lecture or after the lecture, when I got the corrections, I give you in the notes that I give you on WhatsApp. That's why I'm not giving you these notes directly because there are corrections in the notes. I will give the correction in this theorem also. When you read this theorem, you will easily understand this theorem because you have all the definitions explained. So you can prepare this. Now let us see the next theorem. Is it clear to all?
मॅडम आमचं जॉईनच नव्हतं होऊन राहिलं आतापर्यंत मला थेरमच नाही माहित
ठीक है. Okay, those students who have joined late, you can read the notes carefully. Also, I will give you the recording of the lecture. From it, you can prepare easily as you have all the definitions explained already. If you have any doubt, you can ask in next lecture. Now we see the next theorem. Let T be a linear operator on a norm-linear space capital X to norm-linear space capital Y. Then T is bounded if and only if T maps bounded set in capital X into bounded set in capital Y. Proof. First, we write what we have given to us. Let T be a linear operator from norm linear space capital X into norm linear space capital Y. Let T be a bounded linear operator. To prove that T maps bounded set in X into bounded set in Y. What we have to prove, that also we write in the theorem, in the proof. Let S, capital S, be a bounded subset of capital X. So there exist constants K1, K2 such that norm of Tx is less than or equal to K into norm of X. Because we have written let T be a bounded linear operator. So that by definition of boundedness, we have norm of Tx less than or equal to K1 into norm of X for all of X belongs to capital X. We gave this equation number 1. And also as X belongs to capital X and S is a bounded subset of X. So that norm of X is less than or equal to K2 for all of X belongs to capital S. Give this equation number 2. So norm of Tx is less than or equal to K1 into norm of X, hence less than or equal to K1 into K2 because norm of X is less than or equal to K2. We can write K1 into K2 is equal to K. Hence norm of Tx is less than or equal to K. That is image of bounded set S is also bounded because X was arbitrary element. An image of every element is less than or equal to some constant K. Hence T of S, image T of S of capital X under T is bounded. Now we prove the converse part of theorem. Suppose that T maps bounded set in X into bounded sets in Y. To prove that T is bounded, consider a bounded set in capital X, that is S1 of 0. This is a unit sphere centered at origin, unit closed sphere, that is, it is a unit closed ball. Hence, by assumption T of S1 of 0, here center is 0, radius is 1, is bounded in Y. There exists a real number K, a constant K, such that norm of Tz is less than or equal to K for all of Z belongs to S1 of 0, that is sphere, unit sphere S, closed unit sphere S. Let X be any non-zero vector in capital X. Any problem? Nutan? Mute your mic. Now let X be any non-zero vector in capital X. And X upon norm of X belongs to unit sphere, closed unit sphere S. Because we know that in 12th standard we have learned if we divide the vector by its magnitude, then it becomes a unit vector. Now by 1. Norm of T of X upon norm of X less than or equal to K. Because we have written norm of Tx is less than or equal to K, where X is any element in S, unit sphere S. Now we have taken another element X and divided it to its norm, that is X upon norm of X. Now X upon norm of X belongs to S. You can use different letter also in place of X to avoid confusion here. So X upon norm of X belongs to now the sphere. So norm of T of X upon norm of X less than or equal to K. Norm of 1 upon norm of X into T of X less than or equal to K. Not subset, it is less than or equal to. By property of linear, because T is linear, hence 1 upon norm of X can be written in multiplication with T of X. T of alpha X is equal to alpha into T of X. 1 upon norm of X into norm of Tx less than or equal to K. Now this is by property of norm. alpha into norm of x is equal to norm of alpha into x. And norm is a positive number, or it may be equal to 0. So that we can write this. Norm of t of x is less than or equal to k into norm of x. 1 upon norm of x goes to right hand side. All of x belongs to capital X. So that it is proved that t is bounded. Hence the theorem is proved. Is it clear to all? तुम्ही बोलत चला, response देत चला. Is it clear to all? Any doubt? Repeat करायचं. Okay. Now the title is completed. Now we see the next title. Write next title, dual spaces with example. For this title, we need, for the theorems in this title, we need some definitions to know. First definition is functional. Functional is an operator whose range lies in a scalar field K. We say functional is an operator because every field is a vector space over itself, and field in functional analysis generally it is R or C, so that we can call functional as an operator. Functional is an operator whose range lies in the scalar field of the domain, where domain lies in a vector space. The linear bounded functional. A linear functional is said to be bounded for each real number C such that x belongs to domain of f. We have mod of f of x less than or equal to C into norm of x. We can write here norm of f of x also, as we know that range of functional range lies in scalar field K, and K is R or C. So that we can use here mod of f of x also, because R and C are finite dimensional, and finite dimension in case of, okay, so that we can write here mod of f of x less than or equal to C into norm of x. Norm of a functional. All the definitions are similar with the linear operators. Norm of f is equal to supremum over x belongs to domain of f. Domain of f, norm of x is not equal to 0 of mod of f of x upon norm of x. Another formula, supremum over x belongs to domain of x. Norm of x is equal to 1 of mod of f of x. Here is a note. A real functional f with domain of f in a norm linear space is continuous and bounded. Next definition is dual of norm linear space capital X. This is a very important definition. Let capital X be a norm linear space and X dash be its dual. If there is a non-linear space pi and the linear operator t from x dash to y, which is 1, 1 and on 2. And norm of t of x is equal to norm of f for all of f belongs to capital X. Next is algebraic dual space. The set of all linear functional on a vector space X over a scalar field K is called algebraic dual of a vector space capital X. A is equal to F such that F are functionals from X to K where F is linear functional. We have seen the set of all linear functionals defined on a vector space X can itself be made into a vector space. This space is denoted by X star. And it's called the algebraic dual space of capital X. Its algebraic operations of vector space are defined in a natural way as the sum f1 plus f2 of two functionals f1 and f2 is a functional S whose value at every x belongs to capital X is S of x is equal to f1 plus f2 into in bracket x is equal to f1 of x plus f2 of x. Similarly, product p of x is equal to alpha into f of x is equal to alpha into in bracket f of x. Algebraic dual, we consider algebraic dual x star. We write in bracket x star and outside the bracket again a star, or here it is denoted by capital A of x star, that is dual of dual, whose elements are the linear functionals defined on x star. We denote x star of x star star, that is x double star, and call it as the second algebraic dual space of capital X. I will do this in notes. Dual space of norm-linear space. Let X be a norm-linear space, then set of all bounded linear functional on X constitute a norm-linear space with norm defined by norm of F is equal to supremum over X belongs to domain of T. Norm of X is not equal to 0. Mod of F of X upon norm of X. Supremum over X belongs to domain of T. Norm of X is equal to 1 mod of F of X. Second dual of vector space X, that is X double star, that we have seen now. If F is a linear function and X is a vector space, also X star is dual of X, that is set of all linear functionals defined on vector space X. Set of all linear functionals defined on vector space X, we call it as X star. That is algebraic dual space of X. So now see, if F is a linear function and X is a vector space, also X star is dual of X. Then the algebraic conjugate of X star is said to be second dual or bidual of X and denoted by X double star. When you will read the notes, you will get cleared this. If F is finite dimensional, the dimension of X star is equal to dimension of X double star. Now we see definition of Schroeder basis. If a non-linear space capital X contains a set En with the property that for every X belongs to capital X, there is unique subsequence of scalars alpha n such that X minus norm of X minus alpha 1 E1 plus alpha 2 E2 plus and so on alpha n En converges to 0. Then the sequence En is called Schroeder basis. If a non-linear space X contains a sequence En, this sequence En with the property that for every X belongs to capital X, there is a unique sequence, not subsequence, only sequence here. There are minute corrections of scalars alpha n such that norm of X minus in bracket alpha 1 E1 plus and so on alpha n En. This tends to 0 as n tends to infinity. Right here n tends to infinity. Then En, sequence En is called shorter basis or only basis for capital X. Now we see some spaces. Examples of some spaces. Space L1, it contains the elements, which is a sequence, x1, x2, and up to so on. This is a sequence such that summation n is I is equal to 1 to infinity mod of xi is less than infinity, where xi belongs to capital R. It has a basis. This is L1 space. Now we see LP space. LP space is set of all sequences x1, x2, and up to so on such that summation I is equal to 1 to n mod of xi to the power p is less than infinity. Where p is greater than or equal to 1. We have a basis also for LP. An example of basis for LP, shorter basis, E1, E2, E3, etc. Where E1 is set of 1, 0, 0, such that only first element is 1 and other elements are 0. E2 has second element 1 and all elements 0. This is the basis for LP. Now we see L infinity space. It is a sequence. It is set of all sequences such that every sequence is a bounded sequence. This is called as L infinity space. Set of all infinite sequences which are bounded. Next definition is isomorphism. An isomorphism of norm-linear space capital X to norm-linear space capital Y is bijective linear operator T from X to Y, which preserve the norm. That is, for all of small x belongs to capital X, norm of Tx is equal to norm of X. If a linear operator is 1, 1 onto as well as it preserves the norm, then it is called as an isomorphism. That linear operator called as isomorphism, and it is said that X is isomorphic to Y. Norm linear space X is isomorphic with norm linear space Y. If there exists a 1, 1 onto linear operator which preserves the norm, that is norm of Tx is equal to norm of X. Both norms are same. Values of both norms are same. These are all the definitions required to study the theorems. Now we see the theorem. Let X is a n-dimensional vector space. Then its algebraic dual is also n-dimensional. If X is n-dimensional vector space, then its algebraic dual is also n-dimensional. Or let X be an n-dimensional vector space and E is equal to E1 to En a basis for X, then here the proof is starting. Let X is finite dimensional vector space. So dimension of, let us see the proof. Let X be a finite dimensional vector space. Let dimension of X is equal to small n. Let capital E is equal to E1, E2 to En, basis, be basis of capital X. Hence, now we define functionals E1 dash, E2 dash up to so on En dash on capital X such that Ei into Ej dash is equal to 1 if I is equal to j. That is E1 into E1 dash is equal to 1. E1 into E2 dash is equal to 0. That is Ei into Ej dash is equal to 0 if I is not equal to j. Then the set, let the set be capital B. We denote it by capital B is equal to E1 dash, comma E2 dash, comma up to so on En dash. This is subset of X star. X star is the dual space. These are linear functionals. So that this set will be the subset of X star. Now consider a linear combination C1 E1 dash plus C2 E2 dash plus and so on Cn En dash is equal to 0 functional. Now you can write this step C1 E1 plus C2 E2 plus and so on Cn En is equal to 0. Is equal to 0 functional. 0 is a 0 functional. And that 0 will lie in X star because even E2 to E1 dash, E2 dash up to so on En dash. This element is set of this element subset of X star. So this 0 function will be 0 in X star. Where C1, C2 to Cn are arbitrary constants. These constants are from field, scalars. Now C1 E1 dash plus C2 E2 dash plus and so on Cn En dash into X of X is equal to 0 because this is a 0 functional. As all EI are linear functionals, so we can write C1 E1 dash into X plus C2 E2 dash into X plus and so on Cn En dash into X is equal to 0. Now take an element X is equal to E1 E2 up to so on En. If there is any correction, I will tell you. So C1 into E1 dash into E1 plus C2 into E2 dash into E2, E1 plus and so on Cn into En dash into E1 is equal to 0. This implies C1 is equal to 0. Similarly, we get C2 is equal to 0, C3 is equal to 0 and Cn is equal to 0. This proves that E1 dash, E2 dash up to so on En dash is linearly independent. So we can write linear span of B is subset of X star. And give this an equation number 2. Does it prove that the set B containing elements E1 dash, E2 dash up to so on En dash is linearly independent? Now we prove L of F, that is linear span of F, is equal to X star. Trivially, L of F is subset of X star. Because we have proved here. In place of F, you can write here B also. So let an element. Now we have to prove X star is subset of L of F. For any element small x belongs to capital X, we can write X is where L of E is equal to capital X and F belongs to X star. For any X belongs to capital X and L of E is equal to capital X and F belongs to X star, we have X is equal to lambda 1 E1 plus plus and so on lambda n En. All of lambda I belongs to K. Ei dash of X is equal to lambda 1 into Ei dash into E1 plus lambda 2 into Ei dash into E2 plus plus and so on lambda n Ei dash into En. I will give you the corrected proof of this theorem. This is equal to lambda I. F of X is equal to lambda 1 into F of E1 plus lambda 2 into F of E2 plus plus and so on lambda n into F of En is equal to E1 dash of X alpha 1 plus E2 dash of X into alpha 2 plus and so on En dash of X into alpha n. So F of X is equal to alpha 1 E1 dash plus alpha 2 E2 dash plus and so on alpha n En dash of X. Hence F is equal to alpha 1 E1 dash plus alpha 2 E2 dash plus and so on alpha n En dash, which belongs to L of F. There is a confusion between F and B, so that I will give you clearly in the notes. So it is proved that X star is subset of L of B. Here it is given L of F. From 1 and 2 we have L of F is equal to X star. But yes, you can write F, but you have to define. F is equal to set of all E1 dash plus E2 dash plus plus and so on En dash. At starting we denoted it by B. So set of all elements E1 dash, E2 dash up to so on En dash. This is a basis for X star. So dimension of X star is equal to small n, because linear span of this set E1 dash plus E2 dash plus plus and so on En dash, linear span of this set is equal to X star. We have proved linear span of the set of elements E1 dash, E2 dash up to so on En dash. We prove that it is subset of X star and then prove that X star is subset of this set. Thus, it is proved that linear span of these elements E1 dash, E2 dash up to so on En dash. This is equal to X star. So, as these elements are linearly independent, so it is proved that set of these elements is a basis for X star. Hence, dimension of X star is equal to finite element small n. Hence, X star is finite dimensional and hence proved. Meeting संपली का? Hello, am I audible? हे कम थांबलाय?
Yes, ma'am.
Okay. There is some technical problem. Those students who have not joined or unable to join can see this in video lectures. I will give the recording and also I will give you the notes. So from notes you can clearly, when you will read it carefully, you will get clear all things. Do you understand this theorem? You read this theorem carefully from the notes that I will give you. And if there is any doubt or you want repeat, then you can tell me tomorrow. So we meet tomorrow. You can leave the meeting. So we meet tomorrow.
Yes, ma'am.